Hello everyone, welcome back. So we're now going from talking about exponents and exponential properties to exponential functions and their graphs. Now, how you define an exponential function, it kind of varies from text to text, but basically this is a case where your input variable is an exponent or part of an exponent. So if you have something like this, if we say if y is equal to some constant times another constant raised to the x power, that's an example of an exponential function. Okay. So what we're going to be looking at today are these specific functions defined by this expression where a and b are non-zero real numbers, but b is positive. B is always positive. All right. So the idea here is, you'll see, is that the one thing I want you to get from this lesson is that graphs change, graphs of exponential functions change a lot faster and a lot steeper than linear functions or lines, okay, or even polynomial functions when we talk about polynomials. Okay, they're known for their rapid rates of change. So let's look for an example with the function y equals 3 to the x. And if we want to plot this, we can start off by plotting a few points. Okay, and what I'm going to do is I'm going to just take these same values of x in all of these. Negative 1, negative 2, negative 1, 0, 1, and 2. And let's see what we get. Well, 3 to the minus 2, remember, is 1 over 3 squared, so that's 1/9. So this is 1/9. 3 to the minus 1 is 1/3. Anything to the 0 power is always 1. 3 to the first is 3, and 3 squared is 9. Okay. So if we were to plot these 5 points, okay, let's say here's 0, 1, and let's say negative 2, 1/9, and then here's 1/3, and then 3 would be way up here, and 9 would be way up here. So the graph, now notice all these points are above the x-axis. There are no points that sit on the x-axis, but it just comes arbitrarily close to the x-axis over here. So the graph is going to look like this. It should go through this point here. That one. Okay, and this continues, of course, up like that. Okay, so just remember this graph on the left, it gets very close to the x-axis, but it never touches it because 3 raised to any real number is always going to be a positive number, and by positive we mean bigger than 0. Okay. Now, if we look at another example, when y equals 1/2 to the x, we have negative 2, negative 1, 0, 1, 2. Okay, what is 1/2 to the negative 2? Okay, well, to do this, we could do all this on our calculator, but this is going to be 1 over 1/2 squared. Remember, that's how we do negative exponents. And then this is going to be 1 over 1/4. And that means we're taking the reciprocal of 4, which is just 4. Okay, so this is actually just going to be 4. You can check that 1/2 to the negative 1 is going to be 1 over 1/2. That's 2. 1/2 to the 0 is 1. 1/2 to the first is 1/2. And 1/2 times 1/2 is 1/2 squared. That's 1/4. Okay. All right. So now, if we plot these points, we see that we almost have the opposite, right? Here's negative 2. Here's 4. Negative 1 is negative 2. And 0, 1. 1, 1/2, and 1, 1/4. Okay. So we have a curve that looks like this. Okay. Notice that this is decreasing, of course, and decreasing where the other one was increasing. And again, this graph does not touch the the x-axis. Okay, so obviously the x-intercepts in both of these would be at 1, or the y-intercepts in both of these would be at 1, and there are no x-intercepts. If we look at y equals negative 2 to the x, first we have to be very careful because this negative is not part of this 2. That is, we're just computing 2 to the x, and we're raising it to the, we're sticking a minus sign in front of it. We are not taking negative 2 raised to the negative x. So maybe I should just say that this is not equal to minus 2 to the x. Okay, these are different. So we're just focusing on this. Okay, so what would let's plot some points here. Okay, so negative 2 to the minus 2 would be negative 1 over 2 squared, or negative 1/4. And you can check that this would be negative 1/2. This would be 1, or negative 1. This would be negative 2, and this would be negative 4. All right. So now notice that all the y values are negative, which is what we would expect. And in this case, you're going to get something like this. Whereas once again, this will be decreasing. This will be decreasing, but it's going to be completely below the x-axis because 2 to the x is always positive. So when you stick a minus in front of it, this will always be negative. Okay, and in this case, the y-intercept will be at negative 1. So that's what we get when x equals 0. Okay. All right. Just look at maybe one more example here. Y equals 5 times 2 to the x. So we do this. Okay. Here we have when x equals negative 2, 5 times 2 to the minus 2 is going to be 5 times 1/4, which is 5/4. 5 times 2 to the minus 1 will be 5 times 1/2, so this will be 5/2. 5 times 2 to the 0 is going to be 5 times 1, which is just 5. And then you can check that the next ones will be 5 times 2, that's 10, and 5 times 4, that's 20. So if we plot these points, we'll be even more like that, right? Well, we have so the points will be over here. We have 5/4. Here's negative 2, negative 1, 1, and 2. 5/4 is a little bit bigger than 1. 5/4, and then 5/2, and then there's 5, and then 10, and 20 is way up here. We have something like that. And I should say that it still continues to decrease on this side, right? And it still stays above the x-axis. Okay, so this is still an increasing function. In fact, the slope is even steeper. All right. Okay, so let's take a break because we have to, and then I'll continue the rest of this in the next video.